so-called quantum mechanics, which is the mathematical description of the particle waves associated with electron movement in atoms. In order to gain an appreciation of the mathematical problem associated with quantum mechanics, we have to first realize the concept of the Heisenberg uncertainty principle. Heisenberg came to the realization that one cannot simultaneously understand the position and the momentum of a very, very small particle moving at nearly the speed of light, which is essentially what's happening for an electron within an atom. The problem becomes if we can freeze the position of the electron at any moment in time, we can know its position quite accurately, but at that point we don't know how fast it's moving, because to know an object's speed it has to move. If we then allow it to move, the fact that it behaves like a wave creates a problem about knowing its position. And so there's a certain degree of uncertainty or error associated with that type of measurement. So, coupling the wave-particle duality concept for the electron with this uncertainty principle requires that we come up with a more rigorous mathematical model than Bohr used to describe the hydrogen atom. And it is this mathematical description and the power of that mathematics that then gives us quite a large degree of predictability when it comes to dealing with atoms and molecules in a modern sense. The mathematics associated with quantum mechanics involves a determination of a so-called wave function. This is a three-dimensional mathematical formula which describes the position of the electron over a period of time, and it also then gives you some indication of the relative energy of that electron wave, and ultimately averaging it over some period of time gives you a sense of the shape of the wave itself. If one were to square the wave function, we would end up with a probability of finding the electron at any one particular location, but it doesn't tell us exactly where that electron is going to be located at any moment in time, hence the uncertainty principle. So, as an example, in comparing the orbital model of Bohr to the wave function model, we have here a picture showing the nucleus of an atom and a number of different orbits that are possible. If we are dealing with a simple orbital in terms of thinking about it in terms of being spherical, on the right hand side here you have a plot of the radius or radial size of an atom, and on the y-axis we have the psi squared, or the radial probability of finding the electron. And so for the hydrogen atom with the electron in the lowest energy situation, the highest probability of finding the electron will be approximately 50 picometers from the nucleus. This would correspond to roughly the n equals 1 orbit that Bohr would have described. However, the wave function also provides that the electron could be at other locations, both closer and farther away from the nucleus, but at lower probability than at 50 picometers. And you'll notice that that probability decreases quite dramatically as you get farther and farther away from the nucleus. In this particular case, there's also a zero probability of finding the electron in the middle of the nucleus where the radius is 0. In order to describe the wave function for a particular electron, we need to know about the so-called quantum numbers. There are 4 of these quantum numbers that are used to describe the wave function. The first of them is the principal quantum number. This is given a symbol of n. This is essentially equivalent to what Bohr used to describe the orbits of an electron in hydrogen. In fact, we should probably be thinking about the orbits not as rings but as shells because they are 3-dimensional. And the second quantum number is called the angular momentum or Azimuthal quantum number. It's given the symbol of lowercase l. The third quantum number is the magnetic quantum number. It's given the symbol of lowercase m subscript l. The reason for that is that the values of the magnetic quantum number depend upon the value of L. And then finally we have the spin quantum number. And this is given the symbol m subscript s for spin. In order to figure out what the possible values of the various quantum numbers are, we need to follow a few fairly simple sets of rules. The principal quantum number, n, can take on values they are essentially integers, and the lowest possible integer value is 1. And these can go up all the way to infinity. So 1, 2, 3, 4, so on and so forth. In essence, the size of the shell or the so-called orbital will increase as the value of n increases, and in essence, the average location of the electron will be further and further away from the nucleus as n increases. So, we sometimes will take the possible values for the n and assign them letters. So the n equals 1 shell is sometimes referred to as the k. The shell, the n equals 2 is the L, the third shell is the M, and the n equals 4th shell is N, and so on and so forth. So following the order of the alphabet. The angular momentum quantum number, L, is dependent upon the value of the n associated with the electron wave. Possible values for L are 0, 1, 2, 3, 4, all the way up to a highest possible value of n minus 1. So, for example, for the n equals 1 shell, there's only one possible value for L, which is 0. Whereas the second shell, where n equals 2, has 2 possible L values. The L could be 0 or 1. And then if we have the n equals 3 shell, there are 3 possible L values, 0, 1, and 2. These values of L are sometimes referred to as subshells. The so-called subshells are sometimes given letter designations. These letters are lowercase, and they begin with the letter S. So in other words, the lowest possible L value of 0 corresponds to the letter S. The L equals 1 value is P. The L equals 2 is D. The L equals 3 is F. And L equals 4 is G, and so on and so forth from there. So within these possible shells, therefore, there are the possibility of different types of subshells. The third quantum number, the magnetic quantum number, is dependent upon the possible L value. This tells you how many individual shapes of electron waves can occur for each of the subshells and their direction with respect to a Cartesian coordinate system. So, for example, if we had an L value of 0, which corresponds to the letter S, it's an S-type orbital, there's only one m sub L value. Okay, so in other words, the m sub L value can take on values anywhere from negative L to positive L. So, since in this case L is 0, there's only one m sub L value, which is 0. Alternatively, if L is 1, okay, that corresponds to a p-type orbital, there are 3 different p-type orbitals. The lowest possible m sub L value is negative 1, and then there is 0, and then the highest possible value for the p orbital is plus 1. In the case of L equals 2, there are 5 possible m sub L values. The negative L would be negative 2, so the first of the m sub L values is negative 2, then we can have negative 1, 0, positive 1, and positive 2. If we continued on to the L value of 3, there would be 7 possibilities there, negative 3, negative 2, negative 1, 0, positive 1, positive 2, positive 3, and so on and so forth. So, each time we increase the value of L, we increase the number of possible orbitals, or the possible values of m sub L, by 2. The final quantum number is the spin quantum number. There are only 2 possible spin quantum numbers for an electron. It turns out that when you place an electron in a magnetic field, the fact that the electrons have spin result in an orientation of the magnetic field generated by this spinning charge, and that essentially creates a little bit of, the electron acts a bit like a little tiny bar magnet. And that bar magnet can be oriented in one of 2 ways with respect to an external magnetic field. So, we say that the spin of the electron can either be clockwise or counterclockwise with respect to this magnetic field. And so shown here are 2 spherical objects representing the electrons, which are then spinning, and this then creates essentially the spinning charge creates a north and south pole, where the directionality of that pole is perpendicular to the spin. Hence, we can represent the spinning electron that is in a clockwise direction as an arrow that is pointed up, and it is assigned the m sub s value of plus 1/2. If the spin is in the opposite direction, then the arrow or the directionality of north to south for the magnetic field would be down, and in this case this is then corresponds to the magnetic spin quantum number of -1/2.